All right, Year 12s, for our revision for chronic and acute adaptations, our test, here's a review of the booklet. So the initial phase of the booklet, which just had definitions and things like that, that's up to you to look in, and definitely is easy to review. But in terms of looking at questions and things like that, here's my take on how things could have been answered. So this extended response, looking at specifically acute responses, it asks for 6 acute adaptations. So I've mentioned the increased heart rate, increased blood pressure, increased breathing rate, increased AVO2 difference, decreased glycogen stores, and increased perspiration. So in terms of the first 3, the reasons why they happen, so heart rate, blood pressure, breathing rate, that is to get more more blood to the muscle cells for aerobic respiration, more oxygen through that blood. Increased AVO2 difference. We're delivering more oxygen to the cells because they need it. So therefore, there's a large difference there. And the glycogen stores will decrease because when we're working aerobically, which the 20k bike ride would be, working in an aerobic system, we break down our glycogen with oxygen. All right, so we're looking here at an oxygen graph. So we're looking here, sprint test, active recovery, so the time sort of elapsing over that graph, that axis, oxygen consumption getting more throughout that axis. So undertook a 400-meter sprint test followed by an active recovery. She completed the test at maximum intensity in a time of 49.3 seconds. So let's look at what term is commonly used to describe the shaded area. So the shaded area on your graph is that bit up there. I would use that area would be described as oxygen deficit because we have an oxygen demand up here, and as our oxygen consumption rises, we're in deficit during that period there. Explain whether Ling exceeded her lactate threshold during the 400-meter sprint test. Look, it's a difficult one to read there, but I would, based on the oxygen demand there, there are no peaks in the oxygen consumption in the data. It could be suggested that Lynn did not reach her lactate threshold. Looking at the oxygen demand line as well up here, the athlete never crossed that, with their consumption meaning they did not pass the threshold. Also, the active recovery phase is fairly smooth there. It's not super long. Those reasons, I'd say she probably didn't. All right, C, which is the following graphs likely to represent Ling's blood lactate level? Well, we know that during active recovery, it's not going to go up. So that eliminates that one and that one. I would think it would be that one there, bottom left. Why, you ask? I'd say directly after that, the athlete might still be producing blood lactate after dropping her intensity briefly, then moving to active recovery. Also, the first part of recovery being a lactic acid debt may see blood lactate levels not actually change as we're replenishing our PC. Then as we start to get to the lactic acid phase, they would start to reduce. So 2 marks there. That's my reasoning. Next question. An untrained athlete took a maximum oxygen uptake treadmill test of increasing intensity until exhaustion. The individual's AVO2 difference was measured throughout. So refer to the following graph which shows the AVO2 difference. So even before reading the questions, we can see here the difference is quite small there, so 15 to 20. And as we go through the test, we can see the AVO2 difference actually decreases because this line here measures the oxygen in the veins. This line here measures the oxygen in the artery. So we can see the AVO2 difference, low to maximum intensity. So calculate the AVO2 difference for the individual intensity X. Intensity X here, so I've gone 20 minus 15. So make sure we're using the units 5 mils per 110 mils difference. All right. B says, with reference to the graph, explain the AV2 difference during the test as intensity increases. So you don't even need to know AVO2 difference and what it means. It just asks us to read the graph. So like we could say here, as the intensity increases, the AVO2 increases. All right. So there's 1 mark. Then using data off the table. So intensity increases, the AVO2 increases. At point X, here the difference is 5. We can see as the intensity increases, point indicated by arrows here is roughly 13, showing an 8 mil per 110 mil AVO2 difference. This suggests that more oxygen is being delivered to muscles for aerobic respiration. All right, knowledge of the content, reading the graph, 3 marks. All right, the individual took a 6-month endurance training program. Describe the change that will occur in AVO2 difference throughout the program. After completing the program, the athlete could expect to see an increase in the AVO2 difference at maximum intensity. So if I take you back to that graph, here, what we might see is that line might actually be lower. Why, you ask? Because if we train, our body would be able to extract more oxygen and deliver more oxygen to the muscles. So if we're having oxygen come through our arteries, going to our muscle cells, we can take more oxygen out of that blood, so therefore the blood that gets delivered back through the veins has less oxygen in it. So this can be due to improved oxygen delivery through capillarization, hemoglobin, myoglobin stores. So there's it's only 2 marks, but we've showed a really good understanding of the content there. Explain one chronic muscular adaptation that could cause the changes that you identified in part C. So you could say increased muscular hypertrophy, more myoglobin, more mitochondria in the cells for aerobic respiration. You could also say increased capillarization of your muscles. All right, so that's a chronic muscular adaptation, the capillarization of the muscles, more pathways to deliver the oxygen. So there's another chance there. Third one, identify how the change would improve the athlete's performance. So we know if the athlete is getting more oxygen to its muscles, it can work aerobically at a higher intensity. So if an athlete in a triathlon was able to deliver more oxygen to their muscles, they could work at a higher aerobic intensity due to an increased VO2 max. This means the athlete may be able to run at a higher meters per second without utilizing anaerobic systems to sustain at higher intensity without fatiguing. 3 marks, good knowledge of the content. All right. So another graph question. As part of the training program, elite kayakers complete a 500-meter kayaking trial, 120 seconds in order to practice the stroke rate intensity to prevent the early onset of fatigue. Look at the following graph. So we're looking at in 20 seconds, 40 seconds, 60 seconds, 80 seconds, 100 seconds, 120 seconds, we're looking at the breakdown of proportion of energy contribution. So back into our energy systems. All right. What's the percentage energy contribution at 20-second mark? That's easy. We just read off there. So 60% anaerobic and 40% aerobic, but it's asking for the anaerobic there. With reference to the graph, explain the interplay of energy systems. So again, another interplay question is good to practice. So I've just been looked at the 3 specific breakdowns. So during the first 20 seconds of the trial, 60% anaerobic and 40% aerobic. Initial 10-second high intensity would be PC, followed by lactic acid system being dominant. The next part, I've said 20 to 40 seconds, 40% anaerobic, 60% aerobic. Could suggest the intensity may have started backing off, although we still have significant contributors from the lactic acid system. The next part, next 20 seconds, 75% aerobic, 25% anaerobic. 24% anaerobic, stating that the head towards working predominantly aerobically, maybe moving out of the oxygen deficit stage. So I have there 5 marks. Again, that's not really an easy one to break down in terms of looking at maybe in a game situation where you can get different movements to look at. But there's 3 parts of the graph that you can look at. You make your assessments of the percentage of anaerobic versus aerobic, and then you can talk about systems. All right. Identify one acute response of the kayaker and explain the advantage. Increased breathing rate. If the kayaker can get more air to the lungs, more oxygen can be extracted and more O2 used for aerobic respiration. Less lactic acid build up to the event. All right. One physiological cause of fatigue could be lactic acid buildup during the higher percentage of lactic acid system contribution. Could be depletion of glycogen, depletion of PC, any of those sorts of things. All right. Another graph. Athlete completes a 10-kilometer run. Who completes in 10-kilometer runs undertook a fitness test involving running with increased speed until exhaustion. So, refer to the following graph, which looks at running speed, kilometers per hour, along here, blood lactate levels along here, and VO2 max, VO2 here. So you can see here as we get to 21 minutes, we have a sudden spike in blood lactate. All right, we can see VO2 here has a gradual increase, and then as we sort of stop there, it gets lower. So, states the athlete's VO2 maximum. This point right here, which is 80 mils per kilo per minute. Let's go back. Sorry. 80 mils per kilo per minute. Use the data from the graph, explain and identify which energy systems were dominant when the athlete was running at the VO2 maximum. So, here, we can suggest that the athlete was running their VO2 max. At this point, the athlete's blood lactate level has risen significantly from here to here. So, we could suggest that the lactate system would be predominant in this time because we might have passed our lactate threshold. Easy there. Alright. Choose 2 adaptations to explain how they could improve the athlete's VO2 maximum. So I've said cardiac hypertrophy. Alright. So that looks at the increased strength of the heartbeat, stroke volume meaning more blood per stroke, more oxygen to muscles, more aerobic respiration, higher VO2 max. Increased capillarization, more blood vessels over muscles, more pathway for blood, more O2 to muscles, more aerobic respiration, higher VO2 max. So you can see those last 3 things, it's the same. We're talking about the same process, all right? We're getting more oxygen to our muscles, more aerobic respiration, higher VO2 max. So that is how we improve the athlete's VO2 maximum. Blood volume is the same. Increased myoglobin is the same. More myoglobin, more extracted oxygen to the muscles, more O2 to the muscles, more aerobic respiration, higher VO2 max. All right. So here, explain which interval session 1 or 2 would be more likely to improve an athlete's VO2 max. I've said number 2, longer efforts 4 minutes and 80 to 90% maximum intensity. We will see the adaptations at session 1, which session 1 focuses more, see here, on 4 times 10 seconds runs. That's going to be our ATP PC system, which doesn't relate to our VO2 max. All right. I refer to the following table, which shows 2 resistance training programs. Program X and Y. So it says explain which program X or Y will be more appropriate for muscular strength. So I've said X, 5 reps, 5 sets, 95% rep, very heavy, and lots of rest between sets. All right. So we can put that there. 2, choose 1 variable and look at overload. Again, this is stuff that we'll look further on, but that's the answer there. And here, chronic muscular adaptations that occur after 6 months of a resistance training program, increased muscular hypertrophy, and I've talked about increased motor unit recruitment there. All right. Explain how a increase in muscular strength may improve the performance of an elite 100-meter sprinter. That would allow us to probably hold more powerful movements mixed with speed. The strength will allow with the sprinter's start, allowing them to hit top speed more quickly. All right, so 2 marks there. Training methods we haven't gone through. All right, make sure you go through that thoroughly. There's lots of stuff around the same type of concept, and the same type of questions will be in the test. So make sure you utilize this tool. Good luck.